Hi everyone, here I will explain a little bit about question 3 in tutorial 7. I won't give you the full proof, I will give you an example to show how this question goes on and what it really means. Okay, let's look at the question first. The question says that given n plus 1 pairwise different values, x0, x1 until xn, they are real numbers. Prove that for any number yi in R, there exists exactly one polynomial p of x, where ai are real numbers, such that pxi equal to yi for I equal to 0, 1, 2 until n. So before I go on, let me explain what pairwise means. Pairwise means if you take a pair of numbers from this n plus 1 many numbers, they are not the same. So what does it really mean? It actually means that all these n plus 1 numbers are different. Okay, now let me give you an example so that you get a better feeling of what this means, what this question means. Let's look at an example with, say, 4 numbers involved. So the first thing you're given is, you're given x0, x1 to xn, right? So now I'll tell you, I give you x0 is 1, x1 is 2, x3 is 1, and x4 is, say, 3. So I give you these 4 numbers. They're real numbers. And you need to prove that for any number yi, there exists exactly one polynomial. So which means you're also given the yi's. For example, I give you y of 0 is equal to y of 0, let me get my pen, is equal to, okay, what number do we want? 5. Y of 1 is equal to 6, y of 2 is equal to 7, and y of 3 is equal to 8. So in fact, you're given the values of x and y's, so that can you prove that there exists exactly one polynomial p of x is equal to a0 plus a1x plus a2x squared plus a3x to the power of 3, such that p of xi is equal to y of I. So in fact, we're looking for this polynomial p of x, so that p of xi is equal to p of yi. So let me write this down first. What it means? It means p of x0 is equal to y of 0, p of x of 1 is equal to y of 1. Go on. And then p of x of 2 is equal to y of 2, p of x sub 3 is equal to y sub 3. Okay. So in fact, we're given this condition. Can we write these polynomials down? Of course we can. For p of x of 0 is in fact a0 plus a1 times 1 plus a2 times 1 squared plus a3 times 1 cubed. What is it equal to? It's equal to y of 0. So here is equal to 5. P of x1 is equal to y of 1. Means we have a0 plus a1 times 2 plus a2 times 2 squared plus a3 times 2 cubed is equal to y1, 6. The third one, a0 plus a1 times 1. Oh, I can't let x3 be 1 because they have to be different. Let's change this number then. I'll let x3 be 4. Okay, good. Then we have 4, then plus a2 4 squared plus a3 4 cubed is equal to y of 2, which is 7. Good. Next, a0 plus a1 x3. X3. What is x3? I need to change this a little bit. So draw x2, x3 is equal to 4, x1, this is 2, and this is 3. Okay, good. So x3 is in fact 3. Good. So a1 3 plus a2 3 squared plus a3 3 cubed is equal to 8. Very good. So these 4 equations, in fact, you're given. And what you're looking for? you are looking for A0, A1, A2, and A3. So what do you have? You have a linear system involving 4 equations and 4 unknowns. So the question is, can you solve for these unknowns? Well, let's see. Now I'm going to write this linear system in matrix form. Matrix form means I put the unknowns here, A0, A1, A2, and A3. And I put the matrix in front of it. So the matrix will be 1, 1, 1 squared, 1 cubed. So that's from the first equation. Secondly, 1, 2, 2 squared, 2 cubed. Third, 1, 4, 4 squared, 4 to the power of cube. And then last one, 1, 3, 3 squared, 3 cubed. So this is your coefficient matrix, which is equal to 5, 6, 7, and 8. So now I hope this looks more familiar to you. This is just a linear system with involving 4 unknowns. So how do we solve A0, A1, A2, and A3? If I call this matrix M, then in fact I have A0, A1, A2, A3 is equal to M inverse times 5, 6, 7, 8. If you know what M inverse is. So question is, when does M inverse exist? Okay, to answer this question, you have to know that one sufficient condition for the inverse matrix to exist is the determinant of M cannot be 0. So, okay, now we have to find out whether the determinant of this M is 0 or not. To answer this question, let's rewrite M a little bit. So I rewrite M to be 1 to the power of 0, 1 to the power of 1, 1 to the power of 2, 1 to the power of 3. Second row, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Thirdly, 4 to the power of 0, 4 to the power of 1, 4 to the power of 2, 4 to the power of 3. And 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, 3 to the power of 3. Good. 3. This is 2. This is 3. Okay. If you do not recognize this matrix, please look up your note or just go Google this one diamond matrix. And you'll find out how to proceed from here.